Hello, chemist. It's me again. Let's finish up that kinetic discussion. Go back to the notes. Where are you? All right. So in the last one, we talked about just the Arrhenius equations and those two theories. We're going to finish up talking about catalysts and some reaction mechanisms. Okay, what in the world is a catalyst? A catalyst is a substance that increases the rate of the reaction without being consumed. It's there at the beginning and at the end. And so if you're really lucky, you can recycle that catalyst and you can keep using it over and over, especially if it's expensive. All right, so what in the world does it do? It changes the reaction pathway to one or more with a lower activation energy. Okay, you can not change activation energy of reactions. Okay, I can't stress that enough. You cannot change the activation energy of a reaction, but you could certainly take a different pathway. You could certainly take a different pathway. So for instance, let's do distance. All right, so from point A to point B, okay, that's where we're trying to go. We cannot change, whoops, we cannot change the distance between point A and point B. So remember, we're talking about rates here. So I want to know, how fast can you get from A to B? You can't change the distance, but you could, I don't know, let's walk. Okay, that pathway would be pretty slow. Maybe you could take a bike. That pathway would be pretty slow, but it did not change the original distance. Okay, so the original activation energy has not changed. We're just taking different pathways. And those pathways happen to have lower activation energies. So it's not a direct comparison because I can't change the distance. So I'm using those kind of interchangeably, but I can never change A to B, but I can choose pathways that happen to have a lower. Ooh, and then we could be really fast. We could take a plane. All right, this is just something I found in one of my textbooks. It's huge. Now beware, I've seen on standardized test the question that says, catalysts speed up a reaction by lowering its activation energy. No, that is absolutely false. But remember, in other classes, unless you're talking about kinetics, that's not the whole point. And so I haven't seen that question written that way in a while, but the technical answer is no. But please don't miss it on a standardized test. So if they say, hey, catalysts increase the rate of reaction by lowering its activation energy, you know the answer is no. But that test is really meant to say by going through a reaction with a lower activation energy. So they are expecting a true answer. Just beware if you take any standardized tests other than the general chemistry test. They won't ask that. Okay. How many types of catalysts are there? Well, there's tons of catalysts, but they come in three types. Heterogeneous, they're different phases than each other. So a lot of times we'll put a metal in some kind of an aqueous environment, okay? Just heterogeneous, it's not the same phase. Hey, what if they're the same? Homogeneous, so a gas in a gas or a liquid in a liquid, something to that effect. Harder to separate out, by the way. Oh, and then nature's beauties. Ah, enzymes. Enzymes. So we used to do a lab, and it was for, I think, the 101 class. And actually, it was for the 102 class. So a little bit lower, more compressed class than what this is. But we used to have them take a certain amount of table sugar. And to one set of table sugar, they would add concentrated acid. So here we have our wonderful sugar in a beaker and a hot plate. And we would put in concentrated sulfuric acid. And then we would turn up the heat. So basically it was boiling concentrated sulfuric acid. And in the other one, same amount of sugar, we took 10 milliliters of spit And one of the enzymes in there is amylase, and then we put that in there. I know it was gross. It used to gross me out completely. This reacted before the lab was done. This one is slow, slow, slow. But it was a great visual that boiling concentrated sulfuric acid was not as effective at hydrolyzing the sugar as just room temperature spit. Okay, gross, but it was a great visual. If you ate a gigantic meal, the HCl in your stomach, if I remember right, is around 2 molar. That's still pretty strong. But if you didn't have the enzymes, it would take, I don't know, hundreds, thousands a year. I don't know what the real number is, but it would take a long time to digest that food without an enzyme. So the enzymes are nature's beauties, and they are hard to recreate in the laboratory. Very hard to recreate in a laboratory. Okay, well, what about surface area? Now, I talked about this back in the solubility chapter. If you have a cube of sugar and you have a teaspoon of sugar, okay, and you put it in water, which one is soluble? That is not the question. So in the solubility chapter, they have the same solubility. It is sugar. But the question I'm really interested in is who will dissolve faster. Well, this one has more surface area. So the water interacts with more of the sugar at a given time. Here, it has to go only on the surface, and when the surface finally dissolves, then it can work its way in. So this one would dissolve the fastest, but that doesn't mean it's more soluble. It just means it dissolved faster because of the surface area. Okay, here is our last concept, and it seems like I'm contradicting myself, but it's a completely different idea. Whoops, go back there. All right. So for our reaction mechanisms, the word mechanism is very important. Okay. It is a set of individual steps leading to the overall. So it's what is exactly happening. This isn't just in a generic equation. I'm trying to show you, I think this has to bump into this to make this, and then that has to do a twirly to do this. Okay. Elementary steps. We think we know exactly what is going on, what reactions, what collisions. Okay, here's the part where it seems contradictory. For elementary steps, the rate law is the coefficients in the equation. So if this was, look out for the terms mechanism, look out for the words slow, fast, elementary. Okay, if you see any of those words, you know that this is a specific mechanism that we know exactly, and then the coefficients become the exponents. I know, we just learned the other way, okay? But it's very specific to mechanisms in elementary steps. There's something called molecularity that we'll use later on in organic if you're with me. But unimolecular means really it only depends on one reactant. Bimolecular means it's relies on two reactants, and molecular, yeah, you'd think they'd call it tri, but okay. It relies on three. Ah, so compare and contrast. A generic equation, let me see, do I have enough room? I'm just going to come down here. All right, so here is a generic equation. A plus B goes to C. Its rate law has to be determined experimentally. But If I know A bumps into B and forms this complex, okay, and then that complex, oh, what does it have to do? It has to fold over on itself and make this, and then that complex has to react with another A. Whoops, don't want to put it there. That complex has to react with another A to make, wow, I'm doing a great job, aren't I? Huh, it's not erasing. Oh well. So this complex has to react with another A to go on and form C. This step is really fast. The folding over is very slow, and then this one is fast. Okay, this is not the same reaction as that. It is a visual of each step of what I think is happening. And so the slowest step is called the rate determining step. And it is what drives the overall rate. So the rate law is K, A, B complex. And in case this one, the coefficient is 1, because we know that's who is holding up the whole reaction. That's the difference between generic rate laws and elementary step rate laws. All right, some are fast, some are slow. The rate determining step is the slowest step, and it really is where the true overall speed comes from for any reaction. All right, anything else? I think that does kinetics for us. I'm going to do one more mini video, and we are going to do an entire tie together. All right, until next time, jolly out.